Hi there, my name is Jessica Fey and this is my presentation on the electromagnetic spectrum and electromagnetic radiation. So in this presentation I will discuss the principles and properties of electromagnetic waves, the properties of microwaves and infrared radiation, giving examples, and the uses and hazards of X-ray in medical practice. I will then compare and contrast the properties of visible light and UV light in the context of a crime scene investigation. I will explain some applications of visible light and UV light, and I will discuss the biohazards of UV and infrared radiation and the main effects. So firstly, what is an electromagnetic wave? Well, electromagnetic waves travel in a vacuum at the speed of light, which is 300 million meters per second. They don't need to travel through a medium. There are 7 sections on the electromagnetic spectrum, as you can see, and these include radio waves, microwaves, infrared, visible light, ultraviolet, X-ray and gamma radiation. Wavelength and frequency are inversely proportional, meaning as that one increases, the other decreases. This is because wavelength, represented by the Greek letter here, lambda, is the measurement of the distance between one peak to the next, and the frequency is how many wave cycles there are per second. So as you can imagine, if you have a longer wave, you're going to have less of those per second than if you had a shorter wave. The amplitude is the amount of energy that the wave is carrying, and we measure this from the baseline to the crest or the peak of each wave. And as you can imagine, in terms of surfing in the ocean, a 10-foot wave is going to be carrying more water and therefore more energy than a 1-foot wave. Wave velocity, and that can be calculated by this equation here, this triangle equation, and we have velocity at the top, frequency here, and wavelength here. You can also calculate, say, the wavelength by dividing the wave velocity by the wave frequency. You can't have electricity without magnetism. So if we were to see an electromagnetic wave, it'd look very much like this. We'd see 2 elements of the wave, the magnetic field in one plane and the electrical field in another plane perpendicular to this. Electromagnetic waves consist of photons, which are small packets of energy constantly moving, and they're described as the basic unit of light. Properties of microwaves and the examples. So microwaves fall on the scale between radio waves and infrared radiation. They have a relatively long wavelength, that between 1 millimeter and 30 millimeters. Microwaves heat food by causing the molecules, like water within the food, to vibrate, and this causes localized superheating, which is why it's always important to stir our food after we heat it in the microwave. As the FDA website states, microwave radiation is a type of non-ionizing radiation, meaning it doesn't have enough energy to knock an electron from its electron shell up to the next one. Microwaves, unlike infrared, can pass through glass. Microwaves, Bluetooth microwaves, can connect to other Bluetooth signal receivers, making them more versatile than infrared radiation, which needs a specific infrared signal receiver. Examples of uses of microwaves are satellite signals, Wi-Fi, mobile phone communications, Bluetooth, and microwave ablation, which is a newly introduced, minimally invasive way that surgeons can target and remove certain unwanted tissues, such as cancers, from patients. Also, microwaves travel in straight lines, and that can be up to 30 miles, but this can be extended by satellite linkages. Properties of infrared and examples. So these have wavelengths shorter than microwaves at between 700 nanometers and 1 millimeter. Any objects or living things that give off heat are emitting infrared radiation. They're also known as thermal waves and are not visible to the naked eye, yet we can feel the heat that they carry. Infrared cannot travel through glass like microwaves. Infrared signals are unidirectional and can transmit up to 5 meters, although Bluetooth can transmit up to 10 meters, perhaps making that more superior. Infrared signals can only be interrupted by something in the line of sight whereas Bluetooth can be interrupted and intercepted by many things, making infrared perhaps safer security-wise. Infrared connects to one specific receiver, as I before mentioned, compared to Bluetooth, able to connect to multiple receivers, enhancing security for infrared perhaps. The uses for infrared include medical infrared saunas to reduce blood pressure, remote controls, infrared photography. Night vision goggles can detect thermal imaging, which is crucial in search and rescue helicopters and drones where visual light cannot penetrate walls, buildings, fog and curtains and things. The next slide is uses and hazards of X-ray in medical practice. X-ray radiation has a higher frequency wave than the before mentioned electromagnetic waves. It is ionizing radiation, which means it can knock electrons from their shell up to a higher electron shell within the atom. There's a small risk that it can change molecules and lead to cell death and cause a greater risk of developing cancers. In rare cases, it can damage the sperm and egg cells and cause infertility. However, there are extreme benefits to X-rays. It's much easier to investigate any potential breaks in bones, foreign bodies swallowed, blockages such as kidney and gallstones, instead of performing perhaps unnecessary invasive procedures on patients. They can also help to guide surgeons injecting into a joint or when performing a joint replacement to ensure the prosthesis is positioned in the right place. The risks and possible advantages will always be weighed up to decide the best course of action for each patient. The properties of visible light. The wavelength of visible light is between 400 nanometers and 750 nanometers. Visible light on the electromagnetic spectrum consists of the colours we can see, and we can see this when light is refracted or bent when travelling through a medium that is denser than air and slows down the wave. For example, in raindrops, the different wavelengths of each colour are split and are reflected by the water, which we then see as a rainbow. Shorter wavelengths have high frequency, such as the colour purple, and they're refracted more than the longer, lower frequency waves like the colour red, making each rainbow the same pattern of colours, just like in the song. Visible light is known as white light, and this is because all colours cumulative together appear white. Objects appear the colour they do because they're absorbing all of the other visible light wavelengths except the colour that they appear to us. For example, a blue car is absorbing all of the other wavelengths except for that of the colour blue, which it's reflecting back to us. The eye cells, called cones, right at the back of the retina, perceive the different wavelengths as different colours. So that's how we see colours. Some applications of visible light are in telescopes, where a lens refracts the light waves and an eyepiece magnifies the image for us. Fibre optic tubing, using total internal reflection, either in fibre optics in households or medical equipment such as endoscopes. Periscopes to see surroundings from inside, say, submarines. Spectroscopy to analyse a gemstone's purity. To detect the direction a star is travelling in. So if it's coming towards us, the wavelength is shorter and it appears bluer, or as if it's going further away, it's longer and therefore redder. As well as lasers, light amplification by stimulated emission of radiation is what laser stands for. And they are used in printers, medicine, like to operate and cauterize with, and laser eye surgery, and beauty purposes, like laser hair removal, laser tattoo removal, and also by the military. Properties of ultraviolet. So ultraviolet is another type of ionizing radiation due to its shorter wavelength of between 10 nanometers and 400 nanometers. The energy carried by UV rays can excite the electrons, causing them to move electron shell. UV is known as black light. There are three forms: UVA, UVB and UVC. Lots of different items can absorb UV radiation. This excites the electrons, causing them to go up an electron shell, and when the electrons move back down, from their excited state. This emits as a different wavelength, and we see that as light. And the property of this is called fluorescence. So items that fluoresce include fluorescent paints, washing powder to enhance your whites. That's why sometimes in nightclubs white t-shirts and white shirts glow, as well as natural sources like calcite, teeth and sperm. Applications of UV include sterilisation, high-vis PPE, food processing as UV can kill pathogens, curing dental resin, art inspections, and in beauty like tanning beds and acrylic nail curing. So in terms of a crime scene investigation, when you compare visible light to UV, well, visible light was all that the forensics had years ago, meaning if someone had cleaned up blood at a murder scene, the detectives couldn't necessarily detect the blood. But now, with UV black lights, it is possible to detect blood by first making it luminesce by applying certain chemicals to the crime scene. UV is also better than visible light at detecting whether someone was sexually assaulted at the time at the scene, as sperm will fluoresce naturally and can be detected by UV black lights. DNA can be detected and analysed using UV radiation. Finding culprit is less of a process of elimination these days. And then we have the biohazards of UV and infrared radiation. UVA is the type that tans you from the sun, so that has a longer wavelength and a lower photon energy. UVB is used in phototherapy and to treat psoriasis and atopic eczema. It can cause DNA damage and is the main culprit of sunburn and blistering from the sun and can damage the eyes. This has a medium wavelength and therefore a medium photon energy. UVC, however, is the most dangerous form of UV, used in UVC germicidal lamps to disinfect air, water and surfaces. It definitely causes DNA damage. It has a shorter wavelength and high photon energy. Luckily, this type of UV doesn't come through the ozone layer, so we aren't exposed to it in the general atmosphere. UV can potentially lead to cancer later in life, like skin cancers. When it comes to infrared, except for the focused medical infrared lamps that can damage our eyes, the only real other danger from infrared is touching something that is hot. So after that, we've just got some references of the sources that I've used and from the photos that I've used in this. I don't know if you can see that from the photos in this presentation, and then any further reading if you wanted to. And thank you very much for listening.